In this lecture, we are going to discuss some applications of perturbation theory. Now here we are taking the perturbation matrix form. So the problem is find the correction in energies and wave function. If the perturbed Hamilton is given as H is, so this is a matrix is given. So this is your matrix. The elements are 1, 2, epsilon, 2e, 0, 2e, 2 plus e, 3e, 0, 3e, 3 plus e. So this is a perturbation is given. Now, so in order to find the correction in energies, first this Hamilton is split into two parts. One is H naught, which is 1 0 0 0 2 0 0 0 3. So this is the unperturbed Hamiltonian. And another one is H prime. This is a perturbed Hamilton. The perturbed Hamilton is the elements are 0 2 epsilon 0 2 epsilon 2 epsilon 3 epsilon 0 3 epsilon. So here this epsilon is very small, because since this usually the perturbation is very small when compared with the unperturbed Hamiltonian. Now, since this H naught, the unperturbed Hamiltonian H naught is a diagonal matrix, so this is a diagonal matrix. So the eigenvalues are the diagonal elements. So these are the three eigenvalues. So the diagonal elements are 1, 2, 3. So the eigenvalues are lambda 1 is equal to 1, lambda 2 is equal to 2, lambda 3 is equal to 3. Now the eigenstates are also the state 1, 1 0 0, this is a K2 0 1 0, K3 0 0. So there are three eigenstates corresponding to this eigenvalues. These are the unperturbed Hamiltonian. These are the eigenstates as well as the eigenvalues. This can be written like this. Now our task is we have to find the first order correction energies. So the first order correction energy. Now you first take the first eigenvalue. So here this is W0, which is 1, the first eigenvalue. This is the unperturbed energy corresponding to the eigenstate K1. The first order correction is given us. So this is W1 is the first order correction corresponding to the first state. So the superscript here we mentioned for the state. First state, here this is a first order correction energy. This is by definition, and so this formula that we have already evaluated, Brahim H prime Kt. So the H prime is between the two M. Brahim H prime Kt. Now the state is eigenstate is 1, unperturbed state is 1, Bra 1 and Ket 1. So you have to the H prime you have to evaluate between the two states. This is a Bra 1 H prime Ket 1. Now the state Ket 1 is given as 1 0 0. This is we have already given, and because this is the basis of there are three basis vectors in this space. So first this is 1 0 0, and you put H prime here. This is H prime. Then the Ket is just take its conjugate. So this is a column vector. So this will be a row vector. You once if you multiply, you find this value is 0. So that means the first order correction is 0. The first order correction energy is 0. Now let us take the another eigenvalue, the second state. The second state is lambda 2 is equal to 2. So this is the W0 is unperturbed Hamiltonian, and the energy is 2. And this 2, the superscript is represents for the second state. So now for that state, let us evaluate the first order correction. So W12. So this is the first order correction for the state 2. Now here the unperturbed state is, because here M is given as unperturbed state, so for this state the unperturbed state is 2. You get 2, here bra 2. So again you put H prime here, get 2 is already given 0, 1, 0. So you substitute the values here, column vector, and this is your bra vector. This is a is conjugate of vector 2. This is a bra vector 0, 1, 0. If you multiply the three vector matrices, this is a row vector, this is a matrix, and this is a column vector. You multiply the rest. So this epsilon is the first order correction in energy in the state 2. Then similarly you go for the first order correction, the state 3. The state 3, this is a W0, correspond to the state 3. State 3 is given as 0, 0. This is a column vector. Now the first order correction W1 correspond to the state 3 is 3H prime 3. This is bra 3 H prime get 3 prime. So once if we evaluate, we will get the first order correction. So this is 0, 0, 1 is a column vector, and it's a conjugate. This is a bra vector. So this is H prime. Once if we multiply, again we will get it. So the epsilon is the first order correction energy for the state 3 also. Now let us evaluate how to find the second order correction. So W2 is the second order correction. This one represents for the first level. So W2 1. So this is the second order correction for the level 1. So this is your the expression for the second order correction. This is bra m H prime ket n mod square divided by E m minus n. The summation over n prime, prime indicates n should not be equal to. That is the meaning of the prime. M is the unperturbed energy. Now here the unperturbed energy is the E1, and the n runs from the other states. So first term is this m is equal to 1. So n must, this n should not be equal to m. So you have to choose n is equal to 2. So alright. So 1 H prime 2 mod square, then divided by E1 minus E2, because n is equal to 2. So this is the energy corresponding to that level. Again, because you have to make a summation over n, so the next value of n possible is n is equal to 3. So n this m is equal to 1 is a constant term. So 1 H prime 3. So previously we have chosen 2. This is 3 mod square divided by, again E1 is an unperturbed value E1, and the state n must be E3. Now you substitute the value of 1 H prime 2. 1 H prime 2 is, this is the bra vector 1 H prime ket vector 1. Once if we multiply these values, we will get 2 epsilon. So you substitute here 2 epsilon mod square divided by E1 is 1. We have already calculated the energy, lambda 1 is equal to 1. So lambda 1 is E1, and here E3, the third level is the energy is 2. So 2 epsilon mod square divided by 1 minus 2 plus, so actually this is E2 is equal to this 2, but once if we evaluate 1 H, so there are two terms. In the first term you have, if you evaluate, you will get this expression, and you evaluate the second expression 1 H prime 3. So this is 1, and this is H prime, and this is the column vector, and this is state 3. Once if you multiply, you will get a 0. So since it is 0, so the second term is 0. So once if we add, you will get minus 4 epsilon square. Minus 4 epsilon square is the second order correction energy for the state 1. Similarly, You can evaluate the second order correction for the level 2 also. So the same expression, this is the formula to evaluate the second order correction. Here, since the level we are choosing is 2, so this 2 and this is m is equal to 2. N must run from the other values except m is equal to 2. So the first one value is 1. So this must be En, therefore this is also E1 r square plus 2h prime. The other values are, because since it is 2, it should not be 2 because n and m must be different. So I have to choose 3. So E2 minus E2. Now again you evaluate this expression 2h prime 2h prime 1. So this 1h prime 2 and 2h prime 1. Once you evaluate, you will get the same value 2 epsilon. You will get the same value, you can easily check. So this is 2 epsilon r square, and this is E2 is equal to the energy value is 2, we have already calculated, and E3 is so again the first term, this is E1 is equal to 1, so this is 1 plus the second term 2h prime 3. So 3h prime 2 and 2h prime 3, once we evaluate, we will get the same value 3 epsilon. So we will get the same value. So 3 epsilon, so we substitute the value of 3 epsilon here. So 3 epsilon r square divided by 2 minus 3. So we substitute, and once we substitute, this will be 4 epsilon square by 1 and plus 9 epsilon square minus divided by minus 1 divided by minus 5 epsilon square. So this is the second order correction to this level 2. Similarly, since we are having 3 levels, so this is the third level, because all are non-degenerate levels, so we are having they are distinct, they are different levels. So if you calculate the second order correction of the third level, again you have to use the same formula, but here m must be 3 because since we are choosing this one 3, so this is m. N runs from 1 and 2. There are 2 values, m is equal to 1 and n is equal to 2. Now 3h prime 1. 3h prime 1, this is 0, we have already evaluated. 3h prime 2. 3h prime 2. So you substitute draw 3h prime and get 2. Once you evaluate, you will get 3 epsilon. So 3 epsilon square divided by this is E3. E3 is 3. E2 is 2. Once you substitute and simplify, you will get 9 epsilon square. So if you summarize the result, now here now so this there are 3 levels, unperturbed levels. W is 0, which is 1, 2, 3. The energy values are 1, 2, 3, and correction, first order correction. W1 is the first order correction. For this level, it is 0. So first order correction is 0, and here there is a small shift here, and here also there is a small shift that we already calculated, W1 2 and W1 3, and here this is a second order correction, and from here with respect to here there is a shift in energy. So this is a minus 5 epsilon square. So with respect to this is plus 9 epsilon square. This is 4 minus 4 epsilon square. So this is a minus 4 epsilon square. Also this is a shift with respect to this level. So the first order correction energy and the second order correction energy that can be calculated for this non-degenerate levels. So the problem is a non-degenerate level. So this is a matrix form. The Hamilton is given as a matrix form. We have to split the matrix into two matrices. One is unperturbed Hamiltonian, another one is perturbed Hamiltonian. First we have to find the eigenvalues of the unperturbed Hamiltonian. So these are lambda 1 is to 1, 2, 3, and the states are 3 states, ket 1, ket 2, ket 3, and from this if you want to calculate the first order perturbation, and you have to you are on the H prime, the perturbed Hamiltonian, the perturbation is given H prime, which is available. So if you evaluate between the unperturbed states, this is here, it is first state, so 1 H prime 1, this is 0, and for the other states, the first order correction for the second states we have calculated, this is epsilon, and similarly the first order correction to the third states we have calculated epsilon. Usually when the first order correction is 0, then we have to go for the second order. When the first order correction is available, we need not go to the second order, because the second order correction is first order correction is very small, second order correction is very small. So if the first order correction is available, we can stop at that particular level, particular value. Once the first order correction is 0, usually you have to go for the second order correction. Now, so for the second order correction, this expression is also available. Using this, you substitute H prime and the values of m and n, suitable values, you can calculate the second order second order energy also. So the first order energy and the second order energy for the non-degenerate level can be obtained by this method. The next, we are choosing a problem. So far we have calculated the energies for the same problem. Let us calculate the correction to the wave function. So that is also important. So the first order wave function, the correction to first order is given by this expression. Psi 1 is equal to summation over n prime, n h prime m divided by em minus en. So n h prime m divided by em minus en times en. Now you have to perform a summation over n. N should not be equal to n. That is the meaning of the prime. So in order to calculate the first order wave function, this is the subscript is for the corrections in first order correction for the level 1. So you have to substitute. So n must be this value. This is a level 1, and so here also this must be 1. You have to sum over n. So n should not be equal to m. So the term here is 2, and similarly you have to substitute this is e minus n is e1 minus e2 times u2, because since this is 2, this is u2. And once you perform the summation over n, the other value is, since it is 1, we have already chosen 2, so the next value is 3. So 3 h prime 1 divided by e1 minus 3. So there are two terms, and this into here u3. Now 2h prime 1 we have already draw 2 h prime ket 1. So this state is we have already evaluated. U2 is 0, 1, 0. This is U2, and E1 is 1, E2 is 2. So these values are, you can substitute. Plus here 3h prime 1 we have already 0. So the second time is 0. So once you simplify, well, this is this. So this is the correction of the wave function for the state 1. Similarly, the first order correction in the level 2, that can be also determined by using the same expression. You substitute m must be 2 here, so you have to perform the summation of all n's except n is equal to 2. So 1 h prime 2. So this is one term. Here 3h prime, because this since it is 1, we can't choose 2, so this must be 3h prime. So you have to choose this term. So this is u1 and this is u2. This is, since this is un, so this is u1 and this is u1 and this is u3. So this is u1 and this. Now you substitute here 1h prime 2. 1h prime 2 is 2 epsilon, u2 is 2, u1 is 1, and u1 is 1, 0, 0. So first you have to substitute this value. Here 3h prime 2 we have already evaluated. Substitute the value for this h prime between the two states. We have already evaluated 3h prime 2. 3h prime 2. So that value is 3 epsilon. This is u2 minus u3. This is 2 minus 3. Again you substitute. Your u3 is 0, 0, 1. So once if you make a multiplication of these two and you have to add these two expressions. Once if you add the two expressions, we get this expression. The epsilon may be taken as a constant term. So this is the correction, first order correction in the wave function. So first order correction in the state 1, first order correction in the state 2. Both we have already evaluated. Similarly, you have to find the correction. Sorry, here there is a this must be modified. This is not W1. This is psi 1. So the first order correction in the state 3, this is one. You have to use the same formula here. Here m must be 3. You have to perform the summation of again. So 1h prime 3 divided by e3 minus e1 times this is u1 and this is 2h prime 3 u2, because since it is 2, you have to choose u2 by e3 minus e2, and u1, u2 are the basis, the unperturbed states, 1 and unperturbed states 2. So we substitute here 1h prime 3 is 0, so this term is 0, and this u2 is actually u2 is 1, actually u1 is kept 1, and u2 is kept 2, and u3 is kept 2. So we substitute these values, you will get this equation. So if you get the 3 epsilon can be taken outside, so the remaining value is 0. So you have 3 values. Psi 1, the first order correction for the state 1, for state 2, state 3, that all the 3 values are evaluated. So for the above problem, we have calculated the first order correction energy, first order correction wave function, and the second order correction energy. When the Hamiltonian H0, the unperturbed Hamiltonian is diagonal. Suppose the next problem is, we have chosen taken one problem in which the H0 is not diagonal. So here the perturbed Hamiltonian is given. Calculate the first order correction energy due to perturbation. So here this is your H. This is your Hamiltonian. The Hamiltonian can be expressed in terms of sum of two parts. One is unperturbed Hamiltonian and this is a perturbed Hamiltonian. Here the unperturbed Hamiltonian is like this: 520, 2 h prime 0, 0, 0, 2. So this is not diagonal. This is in the previous problem it is diagonal, but this is not diagonal. So the h prime is epsilon with this factor. Usually the epsilon is very small. So h prime is very small when compared to h0. Therefore the epsilon must be very small. Now here you have to find the eigenvalues. If it is a diagonal matrix, the diagonal elements are the eigenvalues. So you can, in our previous problem, you have easily written the eigenvalues. But here you have to write down the equation, find the determinant h naught minus lambda I, and you have to solve it. So write down the eigenvalue equation, and you have to find the determinant h naught minus lambda I, which is equal to 0, and solve the characteristic equation. Once if you solve this characteristic equation for this h naught, we can easily found the eigenvalues. So here, in order to solve this one, you can use a small trick. So the matrix is of this form: A, B, B. This is symmetric, and this is both are equal. A, B, B, and C. Then the eigenvalues are lambda and A plus B one another eigenvalue, A minus B is another eigenvalue. So the three eigenvalues can be expressed in this form. The matrix is of this form. So the given matrix is given like this. So using this expression, this trick, you can easily calculate the first eigenvalue is 2. This unperturbed eigenvalue corresponding to one state. Unperturbed eigenvalue corresponding to the second state is 7. The unperturbed energy eigenvalue corresponding to the state 3 is 3. So we can easily determine the eigenvalues. Now here you have to find the states, eigenstates corresponding to the 3 levels. For this, you have to solve this expression. This eigenvalue equation: A minus lambda I psi is equal to 0. So this is here A is your h naught. So h naught minus lambda I if the psi is 0. So this is the general expression. Psi there are 3 x, y, z. This is a column vector. So the psi may be expressed in terms of the column vector x, y, z. So for the first eigenvalue, lambda is equal to 2. This matrix becomes like this, and this is x, y, z. And once if you take this row multiplying the column, you will get this expression. So this is the first expression. Second row must multiply with this column, you will get the second expression. And the third row multiply with this one, you will get this expression. Now here, let us solve this equation. So in order to solve this one, we are using a trick. We have to write down the coefficients of x, y, z, and again x. So write down this coefficient in this form. For the second equation, 2, 3, 0, 2. So you write down the coefficients, and you put the z is in between these two, and x in between these two, and y. And you note down this arrow mark. So first you write z divided by 3 into 3, 9. So this is your value, and 2 into 2, this is a minus 4. So this type of evaluation of x, y, z is usually common in solving this equation. So x divided by, and this you multiply, this is 0, 0, and y divided by 0 is 0. Then the column vector, so the vector 1, you put a prime here, x, y, z is, this is you write down the denominator part here, write down the denominator part here, and this is z. Z is 5, and if you normalize this wave function, and you will get this is 0, 0. So this is you have to write down the normalized state. So the normalized state is ket 1. So here, if you have equation of this form, then you can solve this equation by using this small trick. Now for another eigenvalue, lambda 2 is equal to 7. Again you have to find. So lambda, this is lambda is equal to 7. Again you have to use h naught minus lambda I into x. This, the vector is the psi is x, y, z is the column vector is equal to 0. So you have to solve this expression, and you can write down the 3 equations: minus 3x plus 2y plus 0 z is equal to 0, 3x minus 2y plus 0 z is 0, 0x is 0, y minus 5 z is 0. So this is first write down this one. Then you write down the coefficients -2, 2, 0, -2. So you take the two equations and write down the coefficients here. Here the coefficients of these two are identical. So you should not take the other equation. You choose the third equation. So you choose this one and this one because these first two equations are identical. So you choose this equation as well as this. Then this is z divided by 0, 0. So you have to multiply this one. 0 and you have to multiply. So 0 minus 0. X divided by 2 into -5 -10 and this 0. Y divided by 0 minus 10. So you write down this equation. Then you write down the x, y, z in a column vector, and the term within the denominator you write down the first one -10. The term within the denominator in y is -10. You write down the second term here, and z divided by 0. So you write down this here. So -10 can be taken outside. This will be 110. So the normality state is to get 2 is once if you normalize this vector, you will get 110. So you will get the get 2. So similarly for lambda is equal to 3, you have to use the same method. H0 minus lambda I in the x is equal to 0. So you write down this one, write down the equation, and use the same trick that you have used in your previous case. So actually this must be this, you multiply this one and this. So use the same trick, and then you can easily calculate x, y, z. So this is your third vector, and once if you normalize this vector, you will get this root 1 by root 2 minus 1 1 0. So if it is a diagonal, the problem is simple because the diagonal elements are the eigenvalues, and the vectors are 1 0 0 0 1 0 0 0. Whereas if it is not diagonal, and then you have to solve the characteristic equation to find the eigenvalues, and each eigenvalue you have to find the eigenvector by using this method that you have mentioned. So you have to calculate the three states 1, 2, 3. They are the unperturbed states corresponding to the state 1. State 1, 2, 3 are the unperturbed states corresponding to the particular eigenvalues. Now let us calculate the first order correction to the state 1. So this is unperturbed state. You calculate the for the state 1. This is eigenvalue is 2. So W0 is the unperturbed energy corresponding to the level. So this is we have already calculated. Now we want to calculate the first order correction. W11. This is M H prime 1 H prime 1 1 H prime. This is bra 1 H prime ket 1. So bra 1 is we have already calculated ket 1. So you substitute 0 0 1 H prime. Your matrix is available, which is given. Then again you write down the ket vector, and once if you multiply, you will get epsilon. So this epsilon is the first order correction energies. So first order correction in the level 2 is level 2, the unperturbed energy level is already calculated, which is 7. So W12 here first order correction in the level 2. This is 2H prime 2. So you substitute the value of state bra 2 H prime ket 2. Once if you evaluate, you calculate the value. This value is calculated as 2 epsilon. So 2 epsilon is the energy corresponding to the first order correction energy for the level 2. Similarly, the first order correction with the W0, here actually this is corresponding to the third level for the state. So the first order correction, this one corresponds to first order. First order correction energy for the level 3 is 3H prime 3, and this value third state ket 3 is there, bra 3 is here because this is just a conjugate, and this is if it is a column vector, this is a must be a row vector, and this is h prime, and this is your h prime. So you substitute these values and you multiply, you find this is. So you let us summarize the result. For the unperturbed energy for the level is 2, and the state, unperturbed state is 0, 0, 1, and the correction energy, first order correction energy is epsilon. For epsilon, for W0, the unperturbed state, and for the second state is everything 7, and the state unperturbed state is represented by cat 2, which is given like this, and the correction in energy for the state is given as 2 epsilon. For the third state, the unperturbed energy is W0 is 3, and the cat 3, this is a unperturbed state 3, and here the first order correction energy for the third state is 0. So the unperturbed levels are represented by 2, 3, 7, which is the W0 is given. If W is the perturbation, first order perturbation, you add the perturbation to this level, 2 plus epsilon here, so this is your epsilon, and this is 0, and when W0 is 3, it is there is no shift, and when W7 is 7, there is a shift of 2 epsilon. So the total energy here is 7 plus 2 epsilon, this is 3, and 2 plus epsilon. So you can calculate the energy up to the first order. If it is a problem is the perturbation is it is not diagonal. Now let us discuss this problem. This is perturbation theory. This is a degenerate perturbation. Degenerate perturbation. Now, what is meant by degenerate perturbation? Now, let us choose a problem. So, the theory is not given. We will understand this problem through this problem. So, we consider the problem and we will discuss the degenerate theory. Now, the Hamilton is given as like this: B0, 0, 0, 0, IB, 0 minus IB 0. So this is the Hamilton is given like this. Now this is and the perturbation is given as H prime. This is H prime is given like this: epsilon into 0, 0, C, C 0, 0, C 0, 0. So the H prime is introduced, and the orthonormal basis is spanned by cat 1, 2, 3. Now calculate the shift in energy of the various unperturbed levels. Also find the first order correction in the both functions. So this is the problem. Now you take the problem H, and this H minus lambda I. So you evaluate this determinant. So you can get the characteristic equation. So once you solve this determinant, you get the characteristic equation, and if you solve this one, you have 3 eigenvalues. So B is one eigenvalue, another plus B is another eigenvalue, third one is minus. So there are 2 eigenvalues are same and 1 eigenvalue is different. So more than 1 eigenvalues are same, then you can call this is a degenerate level. So so far we have discussed the non-degenerate perturbation theory. All the eigenvalues are different. Lambda 1, lambda 2, lambda 3 are different. For this problem, lambda 1, lambda 2 are both are equal, and lambda 3 is different. This is minus 3. So if the problem is like this, then how to find the first order correction? Now let us take one degenerate value. So this lambda 1 is equal to B. Now again you solve this equation. Actually this is H minus lambda I determinant is equal. So in order to find this one, this is actually we can do this. So instead of doing this one, HCX H psi is equal to lambda psi, where psi is given as x1, x2, x3. So solve this eigenvalue equation. So here this is h is given, your psi is x1, x2, x3, your lambda here is b, x1, x2, x3. Let's solve this equation. So write down take this row, multiply this column, you will get one equation. Similarly, take the second row, multiply this column vector, you get the second equation. Similarly, you can get the take the third row and multiply this column vector, you get the third equation. So you have three equations. Now if you solve this equation, you can find x2 is equal to ix3. So actually there are three equations, there are three unknowns. From this expression you can see there is one independent equation. There are three unknowns and one independent equation. You have to choose two unknowns as an arbitrary values. So you have to choose x1 is equal to a, x3 is equal to c, then x2 is equal to ic. So you choose two arbitrary values, and third value can be obtained from the given values. So three unknowns, one independent. You have to choose two arbitrary values. So a and c are arbitrary values, and x2 may be expressed in terms since x2 is equal to ic. If x3 is c, x2 is equal to ic. The eigenvector is, so the x1 is a, x2 is ic, x3 is equal to c. So the arbitrary values, since they are arbitrary values, now you can choose for your convenience. You can choose a is equal to, this is an arbitrary value, c is equal to 1. So get vector 1 prime is equal to 0, this is unnormalized. So once you normalized, you call this unprimed value. Get 1. Is 1 by root 2, 0, I1. So this is the normalized eigenvector corresponding to this case. And since there are, you can choose the other way also, because these are arbitrary values. A1, choose A1 is equal to 1, C is equal to 0. Get 2 prime is equal to 1, 0, 0. After normalization, we get. So from the previous equation, you can choose the constants A and C. By choosing this, you can get the two states. So these are two states corresponding to the same energy but different states. For lambda is equal to minus b, again this is you can write down on the h naught x is equal to 0, and here is actually h naught minus lambda, here this vector x is equal to 0. Now you take this, multiply this 2b x1 0 x2 0 x3 which is equal to 0. So by writing the equations and using this trick, you can solve this expression. So the constants unnormalized vector 3 is 0 minus 2ib square 2b square, and the normalized vector is, the normalized vector becomes like this, 1 by root 2, 0 minus 1. So the normalized means what? You take a vector, any vector, and you take the bra vector and this must be. So by doing this one process, the normalization constant can be determined. The normalization constant can be determined, and once you substitute the normalization constant, this becomes a normalized vector. it is normalized, this must be. So you take 3 prime. So in this problem you have to choose 3 prime and again 3 prime. You find this value, and this must be made to 1 by choosing a constant normalization class. So that can be. So this is the expression. So this is a standard procedure. So 1, 2 are the orthonormal basis vector for the degenerate levels, whereas this is for the non-degenerate. Now let us we are having an expression like H alpha comma alpha beta. This is the only element in the H matrix. U m alpha comma H prime U m alpha. These are the orthonormal states. So if you want to evaluate H11, alpha is equal to 1 and beta is equal to 1. This is U m1 H prime U m1. So this is U m1 is state 1. And this is 1. State 1 and this is bra 1. So substitute bra 1 and get 1 here, and this is for H prime, and the evaluate will be 0. So H11, this element is 0. Similarly, H12 element means bra 1, H prime, ket 2. So you have to find this one. And once if you substitute this value, you got this expression H12. Similarly, H2 1 is H prime is bra 2, ket 1. So you know this expression of 2 and 1. Once if you substitute, you will get 1 by root 2 epsilon c. H22. This is a 2 and this is 2. So this vector is we have already calculated. So once you substitute this here, you will find this. So all the elements of the H alpha beta matrix is calculated H11, H12, H21, H22. So this matrix is calculated like this: 0, 1 by root 2 epsilon c, 1 by root 2 epsilon z, 0. Now let us solve this characteristic equation by the eigenvalue. So this matrix minus lambda and form the determinant. So this H minus, actually this matrix H minus lambda, H alpha beta, this matrix minus lambda I, and form the determinant. This must be 0. And to solve this one, you can get the characteristic equation. And solving this characteristic equation, you have two values. Lambda is equal to plus or minus 1 by root 2 epsilon c. So one is plus value, lambda 1 is 1 by root 2 epsilon c. Another one is lambda 2 is equal to minus 1 by 2 root 2 epsilon c. So there are two values. So these are the degenerate. So these are the correction energies. So this is the first order correction energy for this level, and this is the first order correction to the another level, which is found to be minus 1 by root 2 epsilon c. So correction up to the first order degenerate level is, so W1 for the first level, this is a W0 is the unperturbed level for the state 1, which is B, and the first order correction is for the level 1 is 1 by root 2 epsilon c. So B plus 1 by root 2 epsilon c. So this is the energy up to the first level. For the another level, actually lambda 2, so W, this is for the second state, but the second is for the unperturbed state is the energy is same. So because since this is degenerate, both are having B. And here the correction is energy, the first order correction is plus 1 by root 2 EC. We have already calculated the correction in the first order energy is minus 1 by root 2 EC also. So this one energy is shifted with the plus of this value, another one is shifted by in the opposite direction, the 1 by root of epsilon. So before applying the perturbation, the energy is B. Both the states are having the same energy, so there is a degeneracy. Once apply a perturbation, the energies are two different distinct values, B plus 1 by root 2 epsilon c, B minus 1 by root 2 epsilon c. Therefore, the degeneracy is removed due to perturbation. So to find the first order correction energy for the non-degenerate level, for the non-degenerate level, the eigenvalue we have already found. This is minus B. For this, we have to use the expression for this expression H prime mm. For the non-degenerate case, this is the expression we have already calculated. The level is 3, so this is a 3 and ket 3 we have calculated, bra 3 we have already calculated, h prime is available. Once if we substitute, this is found to be 0. So for the non-degenerate level, the first order correction is found to be 0. So you have two levels. Unperturbed levels are minus B and B and B. They are degenerate levels. This B, the first order correction is 0. The first order correction is 0. Therefore, after the first order correction, the energy is minus B. Here, the degenerate levels, one is B minus epsilon C by root 2, another with B plus epsilon C by 2. Now, if the energy is 0, first order correction is 0, usually you have to go for the second order correction. So now let us calculate the second order correction. So the second order correction, the expression is this. This is the expression for the second order correction corresponding to level 3. So summation over n prime modulus of m h prime n mod square divided by m is. Now m is 3, the unperturbed level. Here n varies from 1 to 3. 1 and this m and n should not be equal. So here this must be 1, E3, E1. So this is 3h prime 1 mod square. Here 3h prime 2 mod square by E3 minus E2, and 3h prime 3 is not allowed. So we are having only two expressions. Now 3h prime 1, once if we evaluate, this is 0. 3h prime 2, because the state 2 and state 3 h prime everything is available, and this value is found to be epsilon c by root 2. So if we substitute this value here, and this is found to be epsilon square c square by 4b. Therefore, here this is up to second order. So for the first order correction, for the degenerate states, these are the energies. For the first order correction is 0, so you have to go for the second order, and after making a correction, the energies are the total energy is minus b plus epsilon square c square by 4. Now let us calculate the wave function, first order correction wave function. The first order correction wave function, again we have used this formula. So this H11, H12, H21, H22, you write down this matrix. This A1, A2, this is the coefficient that you have to determine, A1, A2, which is equal to, this is the energy, first order correction energy into A1, A2. So once we solve this for this energy, so when W1 is equal to 1 by root 2 epsilon c, you use this formula, you solve this one, you can find the coefficients A1, A2. So you substitute these values, and the constants A1, A2 are written by this expression. And also the sum of the squares, A1 square plus A2 square must be 1. This must be 1, and therefore A2 is equal to A1, so A1 square plus A1 square is equal to 1, A1 is equal to 1 by root 2, A2 is also 1 by root 2, and therefore A1 is equal to 1 by root 2, A2 is equal to, coefficient is equal to 1 by root 2, and therefore the wave function V1, the wave function corresponding with this state may be expressed like this. Summation over alpha is 1 to R, A alpha, U, M alpha, these are the coefficients. R is a R fold, here is a two-fold problem, that's a two-way matrix, the degenerate is 2, therefore there are two values, A1, UM1 and A2, UM. And UM1 is ket vector 1, UM2 is ket vector 2, and A1, A2 we have already determined, which is 1 by root 2, and this is 1 by root 2, and if we take 1 by root 2 as a common term, this is a 1 by root 2 into ket 1 plus ket 2. So this is the wave function. For another energy level, W12 is equal to minus 1 by root 2 epsilon c. Again use the same method, and you have to evaluate the constants A1, A2. By solving this expression, this A1 is equal to minus A2 is equal to minus A1, and the sum of the squares must be 1, by using this one, the coefficients A1, A2 can be expressed 1 by root 2 and minus 1 by root 2. So this for this state, um, the verb function is A1 times M1, A2 times M2. This is UM1 is ket vector 1, UM2 is ket vector 2. A1, A2 are 1 by root 2 and minus 1 by root 2. 1 by root 2 is taken as a common term. This is 1 by root 2. Therefore, once if you write down here, this is the verb function corresponding to this level, and this is the correction verb function corresponding to this one. So, for a problem degenerate case, you can calculate the first order correction energy. For the second order correction, we have already calculated this 0. This first order correction is 0. Then you have to go for the second order. We have calculated the correction energy for the second order, and the correction verb function is also determined for the non-degenerate problems. Then we take one more problem. A system that has an unperturbed state can be represented by the perturbed Hamiltonian matrix. So this is a matrix. Perturbed Hamiltonian E1 0A 0 E1B A star B star E2, where E2 is greater than E1. So this H is given. The quantities A and B are to be regarded as perturbations that are of the same order and are small compared with the E2 or minus E1. Use perturbation theory to find the energy eigenvectors. So the first step is you have to write down the perturbed Hamiltonian in terms of unperturbed Hamiltonian plus perturbation. That is your first task. So write down the H0 in this form, and this is H prime in this form. Now here this unperturbed Hamiltonian, this is a perturbation, but the unperturbed Hamiltonian is found to be a diagonal matrix. So this diagonal matrix problem is easy. The eigenvalues of H0 are the diagonal elements. Lambda 1 is equal to E1, this is E2 and E. So the diagonal elements, and also the unperturbed eigenstates, that is 1 0 0 0 1 0 0 0. So that can be easily expressed. The unperturbed eigenstates can be also easily written. Now here the lambda 1 and lambda 2 are equal, so this is a doubly degenerate level. So if you want to calculate the first order correction energy, you have to use this technique. You first find all the elements of this matrix. So H alpha beta is equal to U M alpha comma H prime U M beta. You choose alpha is equal to 1 and beta is equal to H11 is equal to U M1 comma H prime U M1. So this is 1 H prime 1. Ket 1 brown is available. H prime is also available. Once if you multiply, you find this is 0. Similarly, H12 can be determined. Bra 1 H prime 2. So this is bra vector is available, ket vector is available, H prime is also available. Once you substitute and multiply, you find 0. H21 is also found to be 0. H12 is again found to be 0. H22 0. So this matrix H alpha beta is 0 0 0. All the elements are 0. Now let us find the first order correction. In order to find this first order correction, solve this characteristic equation. So once if we solve this characteristic equation, you will find lambda 1 is equal to 0 and lambda 2. So the first order correction is 0. So the degenerate is not removed. So both are 0, correction is 0, the degenerate is not removed. So if the degenerate is not removed, first order correction is 0, you have to go for the second order correction. So first order correction is 0, then you have to go for the second order correction. Now to find the second order correction to the degenerate case, so this expression is available in the text. We are not deriving this expression. You can just refer a text, for example, quantum analysis shift. If you refer, you can take this determinant So you take this determinant, and this is here n should not be equal to m. So the prime indicates n should not be equal to m. So here this W2 is the second order correction. This is once if you solve this determinant, you can find a W2 second order correction. Here E M1, this is M corresponding to 1. This is E1 for the second level. This is also E1 because this is a degenerate sheet, and the third one is only different sheets E2. Now if I substitute these values here, E1 minus E3, here E1 minus E3, and here 2H prime 3, 3H prime 1, 2H prime 3, all the matrices that we have already evaluated. So 1H prime 3 is here, this is A, 2H prime 3 is B, and the substitute this matrix because H prime is available, get vector 1, get vector 2, everything is available. Once if we substitute, and if we substitute this value here, and if we solve, this is the determinant, you have to evaluate this determinant. Once if you evaluate this determinant, and get this expression. This is your characteristic equation. Solving this, you have two equations. W2 is 0. The second order correction to the first state is 0, and another one will be the second order correction to the second level is mod A square plus mod B square by E1 minus E2. So the energy up to the second order for the degenerate states. So for the first state, the unperturbed energy is E1. For the second level, unperturbed state is E1. Both are degenerate states. First order correction here is 0. For the other level, second level is also 0. For the second order correction, here it is 0. Whereas here there is a mod A square plus B square by E1 minus. So now the degeneracy is 0. So this is E1 up to second order. This is E1 plus mod A square plus B square by E1 minus A. So this can be expressed by one is E1, another one is E1 minus, because since E2 is greater than E1, you write down E2 minus E1, so there is a negative sign. So you will get this. Now we have there is a degenerate level also. Degenerate level, the energy is E2 as usual. The expression for the first order correction is this mh prime. This is state 1. First order correction corresponds with state 3, 3h prime 3. 3 is available, cut 3 is available, draw 3 is available. Once you substitute 0, 0, 1, 0, 0, A, 0, 0, B, A star, B star, 0. This is h prime. And this is get vector. Once if you find this value is found. So the first order correction is 0 for this level. If the first order correction is 0, then we have to go for the second order correction. This is the expression for the second order correction. N should not be equal to n. Now you have h prime 3 1 mod square divided by E3 minus E1. Another one is m must be 3, n must be, since we have chosen n is equal to 1 here, n is equal to 2. So this second term, n and h prime 3 3 is not allowed because n should be very different. So you have only two terms. So h prime 3 1 we have evaluated. This is mod A square. This is E3 is E2. This E2 is your E1. And this is h prime 3 2 mod square is mod B square. And this is E2 minus E1. If we simplify, we will get this expression. So the total energy up to second order is this is the unperturbed energy plus 0 is the first order correction. The second order correction is this mod A square plus mod B square. Now so far we have calculated the first order correction for the degenerate level and the second order correction to the non-degenerate level. And this can be easily checked. So you take this, how to check this one? You take the unperturbed Hamiltonian, solve this determinant h minus lambda. So this h minus lambda, once we solve, you have the characteristic equation. So easily check this characteristic equation. And here there are two values. One value is lambda is equal to u1. The rest of the equation becomes like this. So the the characteristic equation becomes like this, and if we solve this characteristic equation, we have two values: E1 minus mod A square plus mod B square by E2 minus E1, lambda 3 is E1 plus mod A square plus mod B square by E1. So these are three values. One is lambda, one is so these are the three eigenvalues, the energy eigenvalues by solving this matrix. So using the perturbation theory also, we have calculated energy up to the second order, and that expression is the same as the these values. So it agrees well. So the second order perturbation theory, that result agrees well with this result.